about what we were talking about before. So I work for DLM, the Dynamic Learning Maps Project, and we treat latent variables as not continuous things. We treat them as categorical. And so when they're treated as categorical, it's like people are either masters or not, right? So there's absolutely no score. There's a high group and a low group. And so in me telling all the psychometricians that work for each of the states, there's 19 states, I had a conversation trying to teach them what it is. I started with this, exactly how I told you. Remember I said there's no score? This is what I think about when I hear that. This is from the Matrix. I cannot...
Do not try and bend the spoon. That's impossible. Instead, only try to realize the truth.
What truth?
There is no spoon.
There is no spoon?
Then you'll see that it is not the spoon that bends. It is only yourself.
This is his serious face. Yeah, see? There is no spoon, there is no score, right? That is what I'm trying to get you to think about. It's like, so The Matrix is a good analogy for it. I saw The Matrix. I'm not a big sci-fi type fan of movies. I was dating a woman in grad school, and she's like, I think you'd like this. So I watched it on TV. And I was like, wow, that's amazing. Yeah? No?
He's never seen it.
You've never seen The Matrix? It's cool. That's cool. I wouldn't normally go pick it out myself, but she made me watch it, and I was like, okay. That was awesome. So it's like that, when you watch it, sorry, Jake, you'll learn that there is like what you think of, it twists your mind for what reality is, and I feel like that's the analog to what we're doing with scores. We use test scores all the time, but really, remember, what we're using isn't real. Right? It isn't real at all. That score, if it were to be existing, is really just an estimate from a distribution of possible scores that could happen if a bunch of assumptions are true. Whoa, right? So your GRE score? That's not real. You just paid $300 to get a not real result. How do you feel about that? Essentially, you said to the GRE, I have missing data. Can you help me find it? And the GRE said, well, we'll give you a try. We'll try it. Make it sound all good, right? Anyway. So yeah, there is no score. All right. Sorry. Should I bring more Matrix into the class? Would that be better?
Yeah.
See, because there was a scene I normally play. I didn't play it this time, but when we started talking about matrix algebra, there's a scene from the Matrix where he's trying to read the matrix. You know what I'm talking about? It's like I don't even see the matrix anymore. I see, black hat or something like that, blonde, red dress, something like that, and it's like the same thing with matrix algebra. It looks all crazy in like a different language after a while, but after you stare for it and use it for a bunch, you don't even see like the numbers anymore. Oh, that right there, that's a covariance, and oh yeah, this is an inner product. Okay, I understand what it's doing. So it's reading it the same way people would read a different language. So it's a pretty interesting. Anyway, yeah, one of the few sci-fi movies I like. Way to go. Anyone else like The Matrix? Who would hate The Matrix? It's okay. This is a safe place.
Well, obviously Jake, but...
No, it's fine. The thing about it is, if you ask me the movies I haven't seen, they far outnumber the ones that I have. In fact, even the ones that everybody thinks are amazing, like the 80s movies that are like The Breakfast Club or any of this Pretty in Pink garbage, whatever. Like when it comes to Christmas time, I haven't seen any of the... That one I've seen.
Okay.
That one I've seen. Thank you. Yes. But like at Christmas time, It's a Wonderful Life, or A Christmas Story, or whatever Christmas. I don't even know the names of them anymore. Yeah, I'm just not. So yeah. So don't hate on Jake. You can hate on me. All right. And don't worry about it, Jake. You don't have to see The Matrix now. So it's okay.
But you will see Jake.
All right. There is no score. Let's see if I can bring this back. Clearly, regression and factor analysis is not quite as exciting as movies. Or is it? Anyway, so what we're trying to do is we're trying to just use our factor score in a regression. That's it. That's all factor analysis does. The measurement model is pretty straightforward. Each item gets predicted by it. If we have one factor, it's the one predictor. If we have more than one factor, there's more than one predictor. If this were, a simple linear regression where one item is a path model, what's endogenous? What's an endogenous variable here? Why? Our item. What's exogenous? The thing that doesn't exist. Isn't that amazing? What? We're going to predict a score with something that didn't exist. But yes, we are going to do that. Okay, so the things that differ from is mainly terminology. So factor analysis goes back, believe it or not, before women could vote in this country. How do you like that? No, sorry. Terrible, right? No, actually, there's one method. Spearman-Brown prophecy formula. I think you're doing this in your in Billy's class this week. Those of you taking, was it 921? You're doing prophecies. That was from 1919, right?
Yes.
Yeah, there we go. So there's a reliability formula that people are using before women had the right to vote in our country. Isn't that crazy? Anyway, I like to provide it some context because I feel like that makes it so much more real. Anyway, factor analysis has been around since like the early 1900s at the very least. It probably dates back to the mid 1800s with Gauss and Galton and so forth. But one of the primary places where this started was a guy named Spearman, Charles Spearman, and it was a debate about the nature of intelligence. And so Charles Spearman said, hey, there's one general fluid type of intelligence. That's it. Period. Done. And if I could observe intelligence, this is what I'd get. I'd be able to predict people's scores on items or scores on tests or so forth. And so that is where that showed up. But the names for each of the regression parameters have changed because at the time when you start doing something and it's a little bit novel, a little bit unique, you can't quite know it well enough to map it on to everything that we've done. But now we look at factor analysis, we look at item response theory, we look at regression, we say they're pretty much analogs. They all show up in the same model family, this larger, bigger picture. So that you see different terms. So this thing that we would call a beta weight, we call a factor loading. Right? We interpret it the same way that we would interpret a beta weight, which is, it is the predicted increase in the item response for every 1 unit increase of the factor. So if the factor goes up 1 unit, now what's a unit on the factor? We still don't know. I haven't defined that yet. But if factor goes up 1, a person's response option, so let's think about it. Persons on the scale, if they have 1 more unit of gambling, that means that they're likely to go up, their response choice might go up by lambda, which may put them up to the next category itself. So yeah, different name. That has a factor loading itself. Mu is an item intercept. That still has the same name. It has a different notation now. And here is our regression slope, regression line, just like we did before. Now, the thing about it is the distance between each score and what was predicted by the factor model, if we tabulated those and calculated the variance, that would still be a residual variance. However, we now call that something specifically different in factor analysis. We call that a unique variance. That is variance unique to the item. And so what that represents, sort of, if you think about it, it's how much variation we have and how far off we're predicting, right? So if we predict people with one factor, right, if we're off a lot, we'll have a big E for each person, so we'll have a big unique variance. What that's saying is that the factor doesn't do a really good job predicting the item. What this really functionally does, though, is it says essentially our items don't measure the factor directly or uniquely. Don't measure the factor perfectly. Measurement error. Heard of measurement error before? You can quantify it with a formula like the Spearman-Brown prophecy formula. Or you can quantify it with the amount of residual or unique variance. of the item. Right? So if there was absolutely zero unique variance, we'd have no measurement error. The item itself would be perfectly related to the factor itself. If our unique variance was large relative to our factor loading, we would have very little information from the item about the factor itself. Right? Pretty much everything would be error. So one of the neat things that a confirmatory factor analysis model does, particularly in the context of path analysis, so if we want to go and take gambling and use it to predict something else or predict it with something, that measurement error does not filter through into gambling itself. It's parceled. It gets partitioned into its own spot, and that spot shows up for each item. So that's where the word unique comes from. That is variability unique to the item and not shared with the factor anymore. So in a measurement model approach, so if you're doing factor analysis, if you're doing item response theory, although item response theory, it's less direct what error happens to be. If you're doing some type of different function because your data aren't continuous, you're partitioning the measurement error from your model to build this latent construct. And if you're doing then some type of analysis simultaneous to predict it or to use it as a predictor, you kind of controlled for it or partitioned it into a spot that it's not going to bias your results. So that's the big picture. More big pictures. So CFA is a linear model. And in confirmatory factor analysis, today's class we're only having one factor. In multiple classes we have multiple factors, but what we end up saying is dimensionality is assumed to be known. The number of factors that underlie your items is assumed at the beginning. In some classes, particularly item response theory, you hear about the assumption of local independence. Have you heard of that? Did they talk about the assumption of unidimensionality? That's really not an assumption. It's the same assumption as this. The dimensionality is known and specified correctly. Right? Unidimensionality, for instance, I'm going to say this, those who've taken item response theory, unidimensionality can't be the assumption in a MERT model. You cannot have multiple factors and assume unidimensionality. So therefore, it's really the dimensionality is known. So what I'm trying to say is this: when you go into the thing that puts the C or the confirmatory in CFA, is that you hypothesize the number of factors ahead of time. And if you're right, if the model fits, then you have a pretty good understanding that your assumptions are met. Something called local independence, which basically says that the errors are independent. Your errors on each of the items are independent after controlling for the factor or factors that are part of the study. So, anytime that, speaking of those of you who've taken IRT, it's in the textbook. IRT assumes unidimensionality. That is not true. It assumes the right dimensionality. So, pardon me. I have to say that. I'm looking at my colleagues, my cohort here. So, anyway. Let's see. Let's start here. Let's take a look at our gambling data. And our goal is to measure this gambling tendency factor so that higher levels of the factor would produce higher ratings in theory on each of these items themselves. Okay, that's what the factor analysis is going to say. These models work at the item level. Now, the ideal is the item level. You will see people take scales and put them into factor analyses. You'll see people take anything and put it into their factor analysis. In some respects, the model is kind of stupid, right? Models they're not these intelligent beings that walk and talk like we do, but they are essentially only work on the data you give them. But to make this work the way we want to in terms of scale building, it's the items of the scale that we're talking about that go into it. Our 5 items, then, we will have 5 separate equations for, just like a path analysis would give us. Right. And here they are. F is our gambling tendency. Right? So if we knew what a person's gambling tendency is, we would be able to predict a response to each of those 5 items for that person. So essentially we're doing 5 simultaneous regressions. So that is, if we could observe F, what we called last week a multivariate regression. How many endogenous variables? 5. How many exogenous? 1. Right? So there you have it. Right now, what we're going to start off with, we talked about what each of these terms mean. We're going to assume that each item has its own factor loading, has its own intercept, and we're going to estimate each item's own residual variance or unique variance. Last week we said that went into a matrix called R. We could still call that the R matrix this week. And it would look like this if we did. It would be a diagonal matrix. 1, 2, with all the unique variances for all the items down the diagonal and zeros in the off diagonal. So the next thing we have to do is, this factor doesn't exist, we have to go make some assumptions about it. We're going to assume, for everything up in this class until the very last week of class, we're going to assume the factor is continuous and follows a normal distribution. The question is, what's its mean and what's its variance? We have to set these to estimate it, but let's play this out as if we didn't. Let me just show you what happens, right? Let's imagine we could somehow figure out what the factor mean is, what the factor variance is. The nice thing about this is, because it's all kind of pretend, we're doing make-believe, if you decide to pick, like for instance, we often call the factor mean 0. If you say, I don't want my factor mean to be 0, I want it to be 100. As you would imagine, then that changes it shifts the scale of the factor up from 0 to 100, but in the regression, each of the parameters will shift with it. Right? The factor loadings will shift, they'll change their size. The means, the intercepts will shift along with it. So what I'm getting at is, it seems like a very arbitrary distinction that we have to pick what the factor mean and variance is, but all of the results that we would specify with it would be identical if we were to pick something else, in terms of the interpretation. Right? The numbers themselves, they may change, but the interpretation is the same. And this is where standardized becomes a big deal. I remember standardized says standard units of y per standard units of f or x. So if you were to say Hong Ling wants to pick, sorry to pick on you Hong Ling, but Hong Ling wants to pick a factor variance of 100 and I just want it to be 1, if we both look at our standardized solution, it sets the factor variance of f to 1 and we get factor loadings that are standardized and they're identical. So the big picture, we're going to talk about identification for the next few slides, but what we pick is somewhat arbitrary and it's identical, and it's basically picked by what your use of the scale is. So, here is a path diagram of that, of a measurement model. We have our factor. The thing about path diagrams when you add factors into the analysis is that in the social sciences, the latent variables are described with circles. The observed variables are described with squares. Now, if you're part of the Dynamic Learning Maps project or you're part of computer science and you talk about networks and hidden nodes and so forth, machine learning is the opposite. The things we don't observe, actually everything is a square. They're treated the same. But so be it. For our world, we'll keep them circular, leave a little fudge factor to make that work. There's a factor up here. It has a unique, or has a factor variance. That's how much variation there is in a factor. By the way, we call the factor variance individual differences, right? That's how much people vary on the trait itself. Each of the loadings are represented by each of the arrows. So just like in a path diagram before, when an arrow starts at one point and ends with an arrow at the end of it, that's saying that the thing where it starts at is predicting the thing it's ending at. So we're saying the factor is predicting the score for each of these items. The prediction is based on the factor loadings themselves. Then on the other side, we have the error terms. We don't actually observe the errors, but oftentimes we put them in circles too. There's lots of different ways of notating these things. And finally, if you want to talk about where the intercepts show up, sometimes we get a triangle. That triangle represents the means or the mean structure. This thing drives me nuts, by the way. We try to put so many different circles and squares and triangles into a path diagram that we sort of lose its meaning overall. What this is trying to describe is the distributional assumptions and all of the parameters of the model for those 5 lines. Right, so it's a nice schematic. It gives the right idea. But I don't try to get hung up on it. Really, the story is directly told by the equations. But I mentioned this last week. A path diagram, most path diagrams you see are not models. They're not isomorphic with all the parameters and the distribution. You don't have a one-to-one correspondence of it. So therefore, oftentimes you do not see the triangle. Every time I see the triangle, I think of the dollar bill with that eye in the triangle. What does that represent? I don't know. Does anyone know what that is? Is it the Illuminati?
Are you confirming the Illuminati right now?
I am not Illuminati. I don't even know what you're talking about. So does anyone know what the eye in the dollar bill is? All right, we're gonna have some fun with this.
I have Providence.
Eye of Providence. You knew this, Alan.
No.
No, you Googled it. Well, okay. Okay, Google. Okay, Google. Define Eye of Providence. All-seeing eye. There it is. You see what I'm talking about? That's what I think about right there when I see the triangle on a path diagram. It creeps me out. It just follows me around whenever it's going along. You know what I'm talking about? I don't know. Anyway, maybe you don't have the same problems I have. That's okay. I'm hoping that you don't. But you'll. I am happily strange. I've been strange all my whole life, and I'm hopefully not about to change now. So that eye down there doesn't typically show up until we get to what we call mean structure models, which will show up after spring break. But, you have $1? No. No, I don't want $1. I was going to pull out $1, but then I realized I only roll in 20s. I'm just sorry. I'm just kidding. Sorry. No, I'm just kidding. I know. That's down from my hundies that I used to go with, but yeah, it's just rough. No, sorry. I love factor analysis. I'm trying to keep it a little more lighthearted. I feel like we're all too serious. So I don't want to make that. Anyway, so what does all this do? The path diagram is a picture that's implying this specific model. It is each of the weights show up. So the arrows are really talking about the beta weights, the predictions. So if you focus on that, that's where it goes. The reason I feel like, and this is my hypothesis, we started with circles and squares and arrows, and we were very happy. But as we moved along and learned more and more about the methodology we were using, the circles and squares and triangles, or circles and squares and arrows, all, believe it or not, represent things that go into covariance matrix in a multivariate normal distribution. But eventually we started putting things in the mean vector, and we had nowhere to put them. So that's where the triangles came about. And then believe it or not, now we have these mixture factor models, and that just shows up as another circle, and that thing should probably be an octagon or something else, right? There's all sorts of weirdness to it. So what's happening is you're looking at a relic of the 1970s, really, when we really didn't talk about the mean vector for most of this. We only did factor analysis in the abstract. And now when we start bringing the mean vector back in, particularly for the methods of estimation that we're using in this class, something called full information, maximum likelihood, we have all the data used in the analysis, it needs to be there. And so that's why the path diagrams start to lose their luster for me. They were built on things that we didn't fully understand, and now, they're pretty though, right? In my previous job, my class would always tease me. I'd say, well, that's not a model. Circle plus square does not equal triangle. Right? It's a conceptual diagram. Anyway. So we're going to assume, like with everything else that we've assumed in this class to this point, we're going to assume a multivariate normal distribution for the factor. We're going to assume a multivariate normal distribution for the errors on each of the items. And when you combine those two together, what we actually get is a multivariate normal distribution for the data. So this is that one time, that one exception, that conditional normality becomes marginal normality. It's when all the things are normal involved in the equation as itself. So each of the things are normal. So this thing is everything that's a variable. These two things are variables. These two things are constants. Those imply a multivariate normal distribution for our data. So just like we started in the class when I showed you all those matrices and I said, okay, it's ugly and terrible, but this is saying what the covariance matrix should look like. Same thing here. Telling us what the mean vector and the covariance matrix should look like. So how do we figure out what it should look like? I'm going to skip through this pretty quick, but we can use what's called the algebra of expectations. This is how it works with path analysis too, although it's a lot harder. If we were to go and say, what is the theoretical mean of an item, right? we could theoretically derive it from the equation itself. Right? The mean is an expectation. We'd say, what is the expected value? How that works is the following. Do you remember what happens if you have data, if you're in an intro stat class and you just have a sample of data, let's say the mean is 10, and I told you, add 3 to everybody's score, everybody's data. What's the mean do? Moves up by 3, right? That's what this is saying, right? If I look at this, I see the mu is a constant, so that really just comes out by itself. Lambda is a constant. It's going to come out eventually, but we want to multiply it by the mean of the factor itself. And then this error term is variable, but it has a mean. So what we end up saying is the mean for the data is the predicted value based on the model. So our mean vector, when we specify a factor model like that, looks like the following. If we were to plug this into the d-norm function, we'd see that our mean vector, the part that would go in the second argument to it, would be equal to the item intercept for each item plus the factor loading times the mean of the factor. So when, and pretty much always, in every analysis we're going to do at the beginning, the mean of the factor is going to be 0. So when the mean of the factor is 0, we're left with the item intercept, which is actually just going to be the mean of the data for the item. And this is why the means were thrown away back in the 1970s. We could figure them out perfectly. All right, we don't need to estimate those. They're throwaway concepts. It's only now that we understand the connection of factor analysis to all the other linear models we do that we understand mean vectors are essentially predicted values. How that goes. Same thing we could do with the item variance. It's a little more complicated, but for each item, we get down to the following result. For one factor model, the item's predicted variance is the factor loading squared times the factor variance squared plus the unique variance. So there's a portion due to the factor, and there's a portion due to the item itself. In the very first incarnation of factor analysis, I think we used to call this thing communality, with the portion due to the factors. Anyone ever heard that term? Probably correct on it. That's how things that are in common are shared, whereas this second part is unique to the item. So the factor model is telling us the mean should be the mean of the data, usually. The variance should be part due to the factor and part due to the item itself. What about the covariance for each of the items? And we could use mathematical statistics and algebra to get to it. Let me just look at the result. If you want to know more about the statistics, let me know. I have good references, or you come to office hours, I can give you the math stat background to all this. It's a lot of fun. This is literally parsing the model, plugging the model in, and doing mathematical algebra to it to figure out what this should be. But what the algebra tells us is that for any covariance between any two pairs of items, their predicted covariance should be the product of the factor loadings times the factor variance. So now we have a very specific structure for a covariance matrix. In particular, this is our covariance matrix right here. That's all the terms in there are the saturated model. That's all for 5 items. There's 5 variances and 10 covariances, 15 terms. Right? And what we're trying to do with this one factor model is to say that it is equivalent to taking all of our factor loadings, putting them in a matrix, taking our factor variance, putting it as a scalar, transpose of our factor loadings, and then our unique variances. So if our one factor model fits, we should see that our patterns of covariances and variances show up as a function of the factor loadings, the unique variances, and the factor variances. So what does that mean? Let's do a little count here. Actually, let me just, Templin did it again. I hate it when I do that. I don't know how I can do that every class too. Anyway, let me get to this right here. What we're saying is there's 15 model parameters here. 15 in the saturated model, right? That's your unstructured model that's going to get estimated. That's the data. If the one factor model fits, it should fit as well as 15. How many parameters are in the one factor model? Well, if we were just to count this, we'd have 5 factor loadings, 1 factor variance, and 5 unique variances. So instead of 15, we'd have 11. And so what we're going to do in estimation is only estimate 11 things, but stretch them onto the 15 that should be there to see how well where we get our estimates, how well they fit as well. So that's ultimately what's happening. Our factor model is a hypothesis. If the hypothesis is true, our covariance matrix should look like this. That's where this lambda phi lambda transpose plus psi. I've actually seen this as a tattoo going form before, but I'm not going to tell you who I've seen that before. Seriously, that's like ingrained in a lot of people. That is one of the more famous quant type equations, believe it or not. In statistics, it goes by the name quadratic form, but it's not all that fascinating in statistics. But in quant psych, that's like, oh, that's amazing. Education, I guess we're in here. I'm a quant person, broadly construed. Anyway, so in this case, if this is a path model, we could do some counting to count up how many parameters we had, and believe it or not, when we add in the mean vector and the 5 means that it had, we had 20 total parameters in our saturated model. In our CFA model, we actually have 17 parameters. There's 5 factor loadings, 5 unique variances, 5 item intercepts, 1 factor mean, and 1 factor variance. So you'd say, oh, check, we've satisfied the identification counting rule, the T rule, so we're good. But the problem actually isn't the factor identification, it's the local identification in this case. We have too many parameters within any pair of sub-equations. It's harder to describe. The math behind this actually is probably beyond what I can understand. So one of the problems is what we need to do is figure out how to identify the factor itself. We need to set its mean, we need to set its variance. So we need to figure out its scale. So here are sorts of ways of doing so. There's 4 different ways that are common. In our class, we're going to only use the default in lavaan, and I'll tell you why in just a bit. But essentially, this 2x2 table breaks down what we're doing. We're going to either set the factor variance or set something in the model so we can estimate it. Or we're going, and so that's one of the things we have to do. The other one is we have to set the factor mean or fix something else, set something else in the model, and estimate. So to estimate, let's talk about the factor variance first. If we start off, actually, let's start off the standardized factor variance with the standardized factor mean. Whenever we standardize something, it's like making a z-score out of it, right? And the z-score has a mean of 0 and a variance or standard deviation of 1. And that's exactly what this is saying. Let's go and set the factor variance to 1. Set the factor mean to 0. We literally go into those parameters and constrain them to be equal to 1 and 0. And you've even done this a little bit in lavaan with other parameters. You've set covariance is equal to 0. I know that in homework too. You may not have set them equal to 1, but you could have. You could put a 1 times them in the analysis that would have set it equal to. So that's kind of the first option. That is often used in scale building. And the reason for that is that it's relatively simple to understand. Right? Everything's on the same scale. In item response theory, often you use this. Your factor is sometimes called theta or ability. And almost more often than not, we just set the mean to 0, ability, the variance to 1. And then maybe later on we rescale it into something that can be anything else, like the GRE score. The default, though, in most programs that do structural equation modeling or confirmatory factor analysis, is to set the factor mean to 0. So it keeps the mean at 0, but it gets an estimate of the factor variance. And the way that we can estimate the factor variance is to set one item's factor loading to a non-zero number, and we usually set it to 1. This is something we typically call a marker item. Right? So we say, oh, item 1, it's usually by default, in lavaan it's default, M plus it's default. The first item that you specify measuring a factor, its factor loading gets fixed to a value of 1, and then we estimate the factor variance. That seems really odd, but that's how it works. To estimate a variance, you have to sort of fix something else somewhere else. And the factor loading, because it shows up in the variance and covariance matrix, particularly in the variance spot, is the easy target for it. So for that item, if you remember what the equation for variance for an item was from a few slides ago, the variance for any item, let's imagine we're looking for the actual observed variance for item 1. The factor model would say it was lambda times sigma squared for the factor plus the unique variance. And so when we set the factor variance equal to 1, we're essentially just saying the factor, the commonality itself is the factor variance for that. Excuse me. So it's a little bit odd. But anyway, that's how it works. The setting one factor loading to 1, we can estimate variance. Believe it or not, these two models, this choice is arbitrary, and the model fit is identical. Right? Whether you fit the one box on the left or the box on the right, your log likelihood is the same. Same model, we've just defined it a little bit differently. And therefore, that means all the parameters are just combinations of each other. We can essentially use the standardized parameters and see the same result in different places. Now, the top line there is less often done. This is where we estimate the factor mean. If you're concerned about group differences in the factor, maybe you want to say there's a difference in mean happiness of men and women. Maybe that first example. We might have to go and estimate a factor mean. And to estimate it, you actually have to take one of the item's intercepts and set it equal to 0. Setting it equal to 0 then allows you to essentially estimate the factor factor mean for all of it, using that equation that you saw on the previous slide. That rarely happens. So let's just forget about it for a moment. Let's do it with one way. But it looks like I'm giving you too much minutia here. Minutia? Too much? Let's do it with the lavaan default here real quick. I'm going to skip past most of this. I'm going to go just give you an analysis as this. All right, so here is Lavaan's syntax. I might come back to the other slides, I might not. The syntax for an item brings about a brand new term in lavaan. For a factor. When we define a factor, so for instance in my syntax I'm defining the gambling factor. To do this in lavaan we need to say put in the equals and a tilde. Right? So tilde by itself is regression. Defining variables that measure a factor is equals tilde. Right? Double tilde is saying there's a variance of something or covariance of something. This is the frustrating thing about lavaan, right? There's tilde, there's double tilde, and now there's equal tilde. And I really don't like the structure this looks like. If this was just tilde, we'd say that gambling was being predicted by all these items. We're not predicting gambling, it's the opposite. We're actually predicting each of the items when gambling. So I really dislike this syntax. So bear with me. Gambling equals tilde. We put each of the items that we think measures gambling on the right-hand side with plus signs in each way. If you do that, if that's all you put into your lavaan syntax, it will estimate the factor model by the default, where the factor mean is set to 0 and the factor variance is estimated because it takes the factor loading from the first item after the equal tilde and sets it to 1. So if you do that, that's all you need to run a factor analysis. The rest of the syntax on my slides are based on all the other terms in the model itself. So once you put gambling in on the right-hand side of an equal tilde, it functions as a variable in the analysis. And you can do anything with it that you would do with any other variable. So we can set its factor mean to 0 by setting gambling tilde 0. That's its factor mean. We could estimate its factor variance by setting gambling double tilde gambling. So now it's in there. But we also have the other indicator or observed variables themselves. We have the estimate of their intercepts, that's what this line does, and estimates of their unique variances, that's what the last lines do. I put all of those in there just to be explicit. Each of those specifies each of the parameters in the model in some way. And if we were to re-identify this, or you identify this with some other type of identification scheme, we would have to go in there and set different things. And I'll show you that in just a bit. So once we do that, we get estimates. Right? Our first... the first set of estimates we get are something under latent variables. These are the factor loadings right here. And you see gambling GRI1, that is the factor loading that's set to 1. That looks a little odd. That seems so arbitrary, right? Again, I'm going to do regression, but I'm going to set the regression slope to 1. So, if only everything could be that way, right? Get a PhD quick. That when you start doing factor analysis or CFA, that just becomes almost second nature. Okay, yeah, we set it to 1, but really, that's just to estimate the factor variance. So, each of the other, but we interpret it the same way. That just means for 1 unit increase in gambling, we would expect the score on the first item to go up by 1 whole integer. Each of the other factor loadings, the estimates are right here. Those are the unstandardized estimates. Right? So they represent the same thing. For a 1 unit increase in the factor, the second item's score goes up 1.2, and likewise for the rest. The item intercepts. These item intercepts, you'll see, are the actual means of each of the items, right? Because we identified the factor with the factor variant mean of 0, and that's what this is telling us right here. Gambling's intercept, or its overall mean, is set to 0. You don't see a standard error, thankfully. You don't see a z-value. You don't see a p-value. It's just 0. 0 mean. So that's somewhat nice. By the way, if you do use M+ for anything, and some people might, it is a nice package for SEM, it will actually put standard errors in of 999.99. So it's just this. It's harder to tell what the identification is when you look at them. But finally, the variances show up. These are unique for the items themselves. These are the unique variances, right? So each item's unique variance happens to be there. But for gambling, that is the factor variance, right? That says people vary in their gambling. The variance of gambling is 0.363. So this arbitrary scale that we've just defined, gambling, has a mean of 0, has a variance of 0.363. That's what we expect people's gambling scores to be around. And so you can do the same type of thing. If you want to talk about where most of this distribution should fall, you've got a normal distribution for gambling. Plus or minus 3 times the square root of the variance should have 99% of the distribution. Plus or minus 3 standard deviations from the mean. How we doing? Yes, Lou.
When you want to choose such a factor variance as 1, and you want to choose your setting of factor loading as
So the reason for setting a factor loading of 1 is because the factor variance, when it's estimated, can change. And the reason why you'd want it to change, perhaps, is because if you were to go and take this factor and predict it with some other variable, that factor variance now becomes residual variance. Right, and so if you, and this is so when we get, and I'm going to show this when we get to SEM a little bit later. But if you remember, my first example of the year, I had marital status predicting overall the latent variable happiness. We could come up with a residual variance. If I had set the factor variance to 1 for happiness there, it would have been 1 in the model without marital status predicting it, and it would have been 1 afterwards. And it would not look like we're explaining any variation to it. In reality, we were, but that showed up in all the other parameters changing. So in the structural equation modeling world, and actually you could do this, I know you're familiar with item response theory, you could do this in IRT as well. You set one discrimination to 1. You can estimate theta's variance. The same thing happens. In SEM, we typically pick this because we like to think of SEM as path analysis with latent variables involved. So if our factor becomes something that's being predicted, it fits. The model fit is the same as if we use a standardized factor, but we often use other things to predict. Other questions? Okay, so what is all this doing? These are all putting those numbers into our predicted variance and covariance. One thing I didn't mention, by the way, I didn't talk about whether the model fit or not, but I'm going through each of these just trying to give it to you. R will draw us a pretty picture. It puts the triangles in. You can actually suppress the triangles if you're like me and get weirded out by them. But it also, the factor analysis itself gives us the model predicted mean vector. Right, these are the means. Here's the mean vector, and if we flip back a couple slides, we'll see that the item intercepts were equal to the means themselves. It also gives us the model predicted covariance, right, matrix. This covariance matrix comes from that matrix product I showed you on a few slides ago. It was lambda phi lambda transpose plus psi. So here's lambda, here's phi, here's psi. You put them all together and you get our factor prediction itself. So that's how it works. Let me flip back a few slides to get to the minutia of the items itself. So here's looking at it with a path analysis. What we've just done is taken the marker item approach where we set one factor loading equal to 1 and we had to estimate the factor variance. The opposite approach would be to say, let's go and set the factor variance equal to 1. We can estimate each of the factor loadings. But then we would also set the factor mean to 0. Right? And this is the same thing on the items. This is with the mean itself. We could set one item. If we wanted to estimate the factor mean right here, we'd set one of the marker item intercepts to 0. Otherwise, this is the case we were just in. We set the factor mean equal to 0, and we estimated each of the item intercepts. So factor means come from item intercepts, roughly speaking. Factor variances come from item variances, essentially. So basically, our data are neither creating nor destroying variation. It's like conservation of variance. I like to talk about that. I know in physics, right, we have conservation of matter or energy. What? Someone help me out here with science. Science is not my strong suit. Sorry. Social science, maybe. Yeah, anyway, conservation of variance here itself. So if we go back to our series of 5 equations, with the marker item, we've set the 1 for the first factor loading, and you saw that in our estimates. And we estimated the factor variance. We set the 0 for the factor mean, and we estimated all the item intercepts. Okay, let's take a break and come back in 10 minutes, and we will continue the fun, although I don't think I'll have the matrix this time.